So, all right, our last problem in chapter 6 has to do with another empirical way to calculate delta H of reaction, but this is using standard enthalpy of formation values. So how do you know that you have a problem that you need to do that? Well, you're going to see an equation that you need to calculate a delta H for, and you're not given a laundry list of other equations that you can manipulate like you saw in our Hess's law problem. Just to remember kind of what that was. This is where we had to figure out a delta H of reaction, and we were given a laundry list of equations that we could manipulate. So in this case, we just have an equation that we want to calculate delta H for. Maybe the problem will tell you to calculate from delta H at values, but if you're not told that, if you're just given an equation and asked to calculate delta H, you're probably going to want to use Appendix B. Now, the caveat for this is each of these species has to be present on Appendix B, or you can't use this method. So here's the equation, and I know this kind of looks scary with kind of these algebraic terms and these sum functions. Really what this basically means is that we are going to take the energy that it costs or that we gain, so this is the gain in energy by forming products, and we're going to subtract off the costs in energy by breaking apart our reactants, right? Because that's what happens in a chemical reaction. We take reactants and we need to break them apart, and we're going to make new products. Generally, that's kind of what we can think about from a concept standpoint in what happens. All right, so what we really need to do is figure out what are the costs of each of these. So what I like to do is have my balanced chemical equation, right? That's key. And what I'm going to do is I'm going to look up on my table my delta HF values. I'm going to put that the units of these are kilojoules per mole, so I can just write the values there. Keep in mind, anytime you find something in its elemental form, it's going to be 0. But let's go through and just kind of look these up. All right, so looking up ammonia, I'm going to want to start with nitrogen because that's the species that's there. So important, we can see that there's 2 values listed for nitrogen, so the phases are important here. This is gaseous nitrogen, so we need to grab the minus 45.9. Again, oxygen, I'll convince you of it here. Oxygen, that's how we find it in its elemental form, so the delta HF is 0. If we look up NO, so again, NO gas, we can see it's positive 90.29 or 90.3. And then H2O. H2O is tough, okay? Because we can find, and we can find it under oxygen here, we can find H2O as gas and as liquid. We got to make sure we grab the right form. This is talking about a gas, so I'm going to round this here minus 241.8. All right, so again, this is the value of our reactants, the value of our products. We're going to find the net gain in this reaction by taking the sum of this and subtracting the sum of this, right? So delta H of reaction is going to be equal to, I'm going to put these in big brackets. We need to qualify this. This is per mole of substance, so I have to qualify that I have more than that. So I'm going to again do products minus reactants. So I've got 4 moles of NO, and I'm going to multiply that by each mole is 90.3 kilojoules per mole. So you can see that's where my units of mole are going to get canceled. Okay, I'm going to add that to 6 moles of water times minus 241.8 kilojoules per mole. So again, this is the net of my gains, right? And so I'm going to subtract, so I'm going to just label these. These are my gains. And I'm going to subtract my costs. So I'm going to have 4 moles here. Write everything in the same here. I've got 4 moles of NH3 times minus 45.9 kilojoules per mole, right? Plus 5 moles of O2 times 0 for that guy. And again, these were my costs. So work out the math for this. delta H of reaction equals minus 1089.6 kilojoules minus a negative 183.6 kilojoules. So again, this is my net worth of products. This is my net worth of reactants. And this is a gain. This is a cost. So delta H of reaction equals minus 906 kilojoules. So again, for the reaction as we have written, this is how much heat is going to be given off. This is an exothermic process. Just as a little heads up, you remember that problem that we did? That was a Hess's Law problem? Problem 6.8? You could do this problem if you just looked up these values on Appendix B. So most problems that are Hess's Law problems, you could also try doing them using the standard enthalpies of formation, but every single one of these species has to be present on this table. And clearly, these are not all the molecules in the universe on Appendix B. So sometimes you'll have to use Hess's Law. But keep in mind, that's also a workaround, is that you can use the standard enthalpy of formation as long as everything is present on your table.